Hello everyone, welcome to the Resonance of Sound or the Speed of Sound lab. We're going to use resonance in order to calculate the speed of sound. Now what we're going to do is we're going to have these tubes and they're going to be closed at one end. When you have a tube that's closed at one end, you'll see that sound will go down approximately 1/4 of a wavelength, and then it will hit a surface and bounce off. When it bounces off of a surface, it inflects half a wavelength. And then the sound is going to go back up the air column 1/4 of a wavelength. So 1/4 plus 1/2 plus 1/4 equals 1 wavelength. When you have the column of air equal to 1/4 of a wavelength, the sound that goes in will come out at a 1 wavelength difference. And as you might remember, that will lead to constructive interference. So it will get louder. And that's where it resonates at that distance. So what we're going to do is we're going to figure out what that 1/4 of a wavelength is. Now what you're going to see is that the actual equation is not just 4 times the length. So we're going to try to calculate the wavelength of sound from our devices. And then if we know the frequency of sound and the wavelength of sound, we can calculate the speed because speed equals frequency times wavelength. Now our wavelength is not just going to be 4 times the length though, because the diameter of the tube actually has some effects as well. So the actual equation for the wavelength will be 4 times the quantity length plus 0.4 or 2/5 times the actual diameter of the tube. Now in this lab we will be using a tube. I had to find my little thing here. We will be using a tube with a diameter of, I measured this, 8.0 centimeters. 8.0 centimeters. So that'll come in handy in a second when we get to the back of this lab and we need to fill in some data. So the diameter of our tube is 8 centimeters. What we need to do is figure out what the length of the tube is, and then knowing the length and the diameter, we can calculate the wavelength. Now, we can already calculate or know the frequency. So here's a little video showing you the frequency of the tuning fork that I'm using. I'm using a B, which is 480 cycles per second or hertz. So if 480 is the frequency that we're going to be using. All right, so that's actually, if I go to the back of this, that's going to be the first column is the frequency. So both of those are going to be 480. So you're going to have 480 as both of your frequencies. Trial 1, trial 2. And you can put 480 in both of those. And the diameter of the tube that we're going to be using is 8.0 centimeters. Now remember that you're going to want to convert everything into meters at some point. So we're measuring these in centimeters, but when we calculate the wavelength down here, we're going to be doing that in meters. Okay, so we have this tube, and this tube will be 1/4 of a wavelength. What I'm going to do is I'm going to take a tuning fork at the top of that tube, and the 480 hertz tuning fork, and I'm going to lift that tube and try to figure out where the distance or length of that tube is 1/4 of a wavelength. So first thing I do is this is my tube. So it's just a big, gigantic tube filled with water. And I have about 8 tubes set up in the lab. And you'll see that I've put a little ruler along the side of it. And that's in centimeters. And it starts from the top. So 0 centimeters is right at the top of this glass tube. Okay? And I can measure down the side of it to figure out how long the tube is. Then what I'm going to do is I'm going to take a tuning fork. You can hear it pretty loud there. And I'm going to figure out how long does this tube need to be until I get kind of a resonance. And you can sort of hear it right about there. Now what I'm going to do now is I'm going to show you that same setup. Only we're going to be looking at it from the level where we can actually read what the length is off of that centimeter scale. Hear that resonance right about there? somewhere in that range. I'll let you choose what that is. This number above it is 14, and the number below it is 15, so somewhere between 14 and 15 centimeters. I'll let you write down what value you think it was loudest at. And I'll play that video through again, just so you can hear that sound. Figure out where you want to put it. So that's what you're going to record under length of air column in centimeters. Now the temperature of this room right now, and we can go ahead and put that in here as well for you guys. You're going to want to put, what was it, 22.8 degrees Celsius is what the temperature was in degrees Celsius today. Okay, so you would put 22.8 in each of those columns, and then whatever value you had for the length of your air column. So that concludes your data. Now you're going to do this twice. So let's look at another. Let's do it again. Not from as, I mean, this is from farther away just so that you can see exactly what I was doing. And so just take a guess of what you think the length was for that one, about where you think the length was. Do it here again. Try to do it quickly just so you can see about where the range is. And let's start that over from the beginning just so you can see it, because I'm pretty sure that's... And I'll try and kind of pause it right about where it is. So like, what do you got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's between 14 and 15 again. So you can kind of, I know it's really blurry, but about what you think that one is as your second trial. Here it is in video form again. You can kind of figure out where about there do you think between 14 and 15 it was loudest. And you can always rewind this video back to where you need it to watch that again. And slow it down and pause it as you need. Okay. So that's our tube. Now just to show you that it's not just that particular tube, here's another same tuning fork on a different size tube. So you can see that it doesn't really matter. Now this one's going to be a little longer, and the reason that it's farther down on this tube is because the tube is not as wide, so it's going to have a slightly different effect. But it's not a lot longer. Really the tuning fork is part of what determines the length. So if I pause that, where were we? We were at like 9, 10, 11, 12, 13, 14. So this was somewhere around 16 centimeters for this tube. It's a little bit longer because the tube is much smaller. Okay. So you have a frequency, a diameter, a length, and a temperature. What you need to do now is use the equation above, and you can write your equations right here that you use. You'll need an equation for wavelength. And then you're going to calculate the speed of sound, which I explain how to do. You don't need an equation for this, but what is the accepted speed of sound? You can look that up. What is the accepted speed of sound at 22.8 degrees Celsius? Or you can use this equation, 332 meters per second at 0 plus 0.6 meters per second per degree above 0. So it'd be 332 plus 0.6 times 22.8. And that would be your accepted speed of sound. Your error is the difference between these two, and your relative error, you should remember, is the difference divided by the accepted times 100%. For each of these, calculate an average. You don't really I don't know why I haven't. I guess you do need the average in the first data table because you need an average length of air column as well, because these two might not be exactly the same. Okay. So that's what you're trying to do, is figure out what the speed of sound is using frequency times wavelength. Do that, and then you have some questions to answer and a conclusion. And if you have any questions, you can let me know.